Okay, so welcome back, everybody who's on the internet. Hello. And then I have to make this go forward so we're at the right slide, because remember we stopped about halfway through. This doesn't have this thing in here. I gotta put this thing in here. Please forget. Okay. Blah, 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 blah. Gotta get all through this. Okay, we were right around density, right? Density here. Okay. So density of water. So density of water, what do I want to say about this? So density, it comes up a lot in our studies of oceanography, so you want to pay special attention to this part, okay? So we're on lecture assignment number 12, and let me get that so I can make sure I hit everything that's on there, lecture assignment number 12. Okay. Now, so what is density? That's the first thing you got to know. So it's the mass of a given volume of a substance. Okay. Normally in this class, we're going to express density. The units that we're going to use for density are grams per cc. A cc is a cubic centimeter. Okay. Another way of writing that is gram per cm cubed. Okay. So there's different ways of writing it. And I just want you to make sure you're familiar with it. Now a cubic centimeter, just to let you know, cubic centimeter, it's like about the size of a dime. Just in case you don't have a sense of how big a cubic centimeter is, I wouldn't blame you. Now another thing I want to tell you, it just so happens that a cubic centimeter is the same as 1 milliliter, okay? So you're going to see density expressed in all these different ways. 1 gram per cc, 1 gram per cubic centimeter, cm with a 3 exponent, and 1 gram per milliliter. Okay, it all means the same thing. Is that clear? Because a milliliter is a cm cubed is a cc. Okay? Everybody follow that? Does that make sense? It's good? All right, so by definition in the metric system, water, its density is 1 gram per cc. Okay, that's just by how they set up the metric system. It's water. It's kind of based on water, you know. So water is 1 gram per cc. That's the density of it. That means that a liter of water is 1 kg. A liter of water weighs 1 kg. All right, here's a question. It's not a trick question. Does ice sink in water? No, it floats. So what does that mean about the density of ice? Is the density of ice going to be greater than 1 or less than 1?
Less.
Yeah, the density will be less. Because things that are less dense float. Okay, things that are less dense float. So that rock that plummeted to the bottom of the water, does that have a density greater than 1 or less than 1? Greater than 1. Okay. So things that have greater density sink. Things that have less density, less than 1, are going to float in the water. Okay. Just to give you an idea, these are some densities of different materials. Okay. So aluminum and copper and concrete and glass and rocks. A lot of rocks have a density of about 2 point something, like 2.7 and 2.5, maybe 3.0, something like that. That's most rocks, okay? So that gives you an idea. All right, one question I have here. Let's see if I talk about this a little bit. Talk about this more. Oh, here's some, I just find this interesting. Here's pure uranium metal. Okay, it has some gloves. 19 grams per cc. It's very dense. But that's actually not the densest material. Platinum is pretty close to the densest material. It's 21.45. So it's like almost 22 times denser than water. So that's platinum. So if you ever see in a movie, and by the way, you know what else is very dense is gold. So if you ever see in a movie, people I always think it's funny because you'll see people holding gold bars, like they're very light. And actually a gold bar, it's so dense, they're very heavy, right? So you can tell they're fake that way. All right, there's just some density at different rocks. You know, notice how pumice is the one that's less than 1. So you can take pumice and it'll float in water, right? So, in case you've never seen that before, people are amazed. Okay. It's a floating rock. So, you know, you also might know that, like, if you ever try to make vinaigrette or something like that, the olive oil or the oil or whatever is going to float on top, right? And that means that the oil has a density that's less than 1 or greater than 1? Yeah, it's going to be less than 1, okay? And usually vegetable oil has a density that's like 0.9 grams per cc, just to let you know. Okay, we got Natalia and Amanda here. Okay, gotcha. Now, if you take a look, I just wanted to show you, this is kind of like an atomic diagram, atom by atom breakdown of how water and ice look at the atomic level, right? So, do you see how when the ice links up that way, it's actually like, it's not so compacted together? Do you see that? Like there's a lot more space in between all of the atoms, and that's why it ends up being less dense. Okay, so ice is less dense, so it's just going to float on water, and because it's less dense, something very strange happens, right? When you freeze water, unlike most materials, and this is very unusual. Most materials do not do this, but you all know what happens. What happens if you put a bottle of whatever, you put a glass bottle of some liquid in the freezer, what happens to that glass bottle? It'll expand and it'll blow up, right? And like, did anybody have burst pipes last February? Not the last February, the February before the Great Freeze. Yeah, did anybody get burst pipes with that? So, maybe not, but that's what happens, right? So if you were to put a bottle of water in the freezer, let it freeze, it expands and it destroys the bottle, right? Cracks the bottle, and it can destroy pipes too. Crack the pipes. Okay, the same thing. Now, ice is 10% less dense than seawater. So that means that when you see an iceberg like this, 90% of the iceberg is underwater. Okay, 10% of the iceberg is above water. Okay, so if you think about this, if that iceberg melts, the remaining 10% of this material is going to go underwater. I mean, it's going to be added to the water. But the material that's under there, that's already submerged, that's also going to melt and become less dense, or it's going to become denser too. So it ends up equaling out. So this is a thing that I want you to realize. It's kind of important for things like climate change, people worrying about climate change. So sea ice does not contribute to rising sea levels. So melting of sea ice does not contribute to rising sea levels. So, and you could actually prove this to you. If you prove this to yourself, you could get a big glass of ice water, fill it all the way up to the brim, ice water, right? Let it melt, and it won't overflow, okay? Because it won't change the level. Because the material that is above the sea level, it's only 10% of the iceberg. And even though, yes, it's going to get added to the water eventually when it melts, the 90% of the iceberg that is underwater is also going to become denser as it becomes. So it doesn't end up changing the net volume, okay? So when people talk about they're concerned about ice melting, they're not talking about sea ice. They're only talking about glacial ice, ice that's on the land, okay? So I kind of wanted to make that clear. So if anybody's worried about icebergs melting, don't worry. It doesn't matter. It doesn't change the sea levels. Okay. It's the glacial ice that you should worry about. Okay, so I just want to show you, this is a global map of seawater density. Global map of seawater density. So the colors that are kind of like cool colors, like purple and blue, those colors indicate relatively not so dense water. Okay, so it's less dense water. The stuff that is red and orangish, that's denser water. Now notice that you can kind of think of this as like the density would be about, so this is actually kilograms per cubic meter, but a kilogram per cubic meter is just 1,000 times a gram per cubic centimeter, and you might be like, what? Don't worry about that. But you can kind of think about this as, put a decimal point right there. Okay, so instead of 1,024, it's 1.024. Okay, so that's pretty close to 1, right? So you notice that the densities here are all just a little bit above 1, right? 1.02 to all the way over here, 1.028, okay? Why is it a little bit higher than 1? In the whole ocean, there, we don't see anything with a density of 1. Didn't I just say that water, pure water, has a density of 1? So why is this a little bit denser?
Not just pure water.
That's right, it's not just pure water. What's in seawater?
Salt.
Salt, right? So the salt makes it denser, okay? So the fact that this is not exactly 1 is because of the salt, right? So can y'all look at this and just tell me, what do you think is maybe making this, any guesses? I just want you to guess and think about it. Why are there some areas that are, looks like around the equator actually, that things get a little bit less dense?
The current.
And then, what's that?
The current.
Currents, that's a good idea. Might have something to do with it. Actually, currents, there are certain parts of this that are denser because of currents. We'll talk about that when we get to currents. Marine life is it's a good guess too. It doesn't make a, so I want you, here's a big hint for you. Think about salt. So what this mostly has to do with is how salty the ocean is. A lot of it's controlled by the saltiness of the ocean. So that's a lot of what you're seeing. So you're actually seeing differences in the saltiness of the ocean. And when we look at salt maps, salt salinity maps, you'll notice it looks similar. But another thing affects density of the water too, and that is the temperature. Temperature, hotter water is less dense, colder water is denser. So density of fresh water, it's kind of interesting, but the density of fresh water, okay, not seawater, but fresh water, actually peaks out at about 4 degrees Celsius. 4 degrees Celsius. And it actually gets less dense in either direction from there. Now for seawater, so what actually happens is kind of interesting in lakes, not the oceans, but in lakes, in like a frozen lake, so think of Lake Baikal, okay, in a frozen lake, let's say. I don't think I talked about Lake Baikal. I think I talked about that in earth science, sorry. Gus should know about that because I teach my earth science class. But the water at the bottom of a lake is often, if it's a frozen lake, it's often about 4 degrees Celsius. So why would the water at the bottom of the lake, at a frozen lake, be 4 degrees Celsius? It's actually warmer than the stuff up here. Why would it be the warmest water in a frozen lake be at the bottom? 4 degrees, and it'll be 4 degrees Celsius. Why would it do that? What's that? Yeah, the density? Yeah, something about the density. We'll go back to this. What is the temperature of the densest fresh water? Can you see that? So what's the temperature? 4, right? So the densest water, where is the densest water going to go in the water column? It's going to go to the bottom. Now you're going to see this over and over and over again in this class, okay? The densest water is going to sink to the bottom. So think about this. Where's saltier water going to want to go? If you make salt, really salty water, where's that salty water going to want to go? It's going to sink to the bottom. Okay, it's going to sink to the bottom. And I'll show you a demonstration 2 weeks from now. It's like, we're not going to be here next week, so I'll show you a demonstration about this. It's kind of cool. You'll like it. It amazed my last class. It was like the last semester or something like that. But anyway, So salinity changes the density, and so does temperature. Temperature changes it too. Salinity makes the density go up, and that's why if you ever go to the Dead Sea, which is in the Holy Lands, Israel, Jordan area, right? It's very, very dense water because it's absolutely saturated with salt. So you can actually do this. See how this is Conan O'Brien, but I just thought it was funny because I was looking for pictures of the Dead Sea and I found Conan O'Brien doing it, so I got him. But you can see he's just sitting here reading the newspaper, easily floating in that water. So why does he easily float? It's because the water's so dense. Okay, so that's why. And you can see that temperature and density, they're kind of related to this global map of temperature, global map of density, global map of salinity. Okay, so these maps, I'm showing these to you right now. They're going to become very important in this class as we move forward. Okay, these global maps of salinity, global maps of temperature. Okay. All right, so, oh gosh, I've been working on 13, haven't I?
Yeah.
I'm sorry. Let's go back and look at 13. I'm like, this can't possibly be just 12. This is not right. I thought I better go check how this goes. Okay, let's go back and let's look at 13 because I've been kind of breezing through this stuff. All right, so where is ocean water? Let's look at this. Where's ocean water densest?
Equator.
Yeah, so, oh no, that's the opposite. The colors are different. So see, that's less dense is at the equator.
Arctic.
Yeah, oh yeah, it's really dense down there in the Antarctic, isn't it? So yeah, near the poles. Yeah, look up there in the Arctic Ocean, it's very dense. You notice randomly it's very dense in the Mediterranean. Do you see that? The Mediterranean Sea?
I know where the Dead Sea is.
Is it salty?
Yeah, it's because it's very salty. It's very salty. Okay. All right. So what are some? So at equator we have relatively less dense. Near the poles we get a little bit denser. Okay. So that might be because of temperature, right? So the equator it's relatively hot water. In the poles it's relatively cold water. Remember that temperature plays a role here. So that brings us to number 2. What are the 2 factors that affect the density of water, ocean water? Salt and temperature. Salt and temperature. Those are the 2 things that really control ocean water density. Okay? Cold water sinks. That's why they have hot air balloons and not cold air balloons. If you had a cold air balloon, it would just sit there. It wouldn't do anything. So hot water rises, cold water sinks, right? Salty water sinks, fresh water rises, okay? So does that all make sense? That becomes very important when we talk about circulation of the ocean, because we're not just going to talk about currents, but we're going to talk about circulation through the depths and the shallows of the ocean too. So that plays a big role because it's all density control, okay? So make sure you got that. So some things that affect ocean salinity, I guess that's kind of the same.
Temperature?
Yeah, those are like the same things. I guess it's just temperature and the salinity again. I don't know what I was thinking with that.
Like what salt in the water?
What's that?
Are you asking that?
Oh, you know what? You know what I might be looking for here? I'm sorry. Probably for number 3, this is what I'm looking for. What are things that maybe are controlling the salinity, the ocean salinity? I'm thinking of ocean density. So what are some things, so number 3, what are some things that would affect the ocean's salinity? So what would make the water, because you'll notice that if you look at salinity, some places have very high salinity, kind of random patches in the Atlantic, seem to have very high salinity. Some things, look, especially around here in the poles, we have very low salinity. What do you all think? What are some things?
Precipitation.
Yeah, so the salt, that controls the salinity directly, but I'm saying what controls the salt? Because I mean the salinity is the salt. So, but it's one, Amanda said 1, so what's that?
Precipitation.
Precipitation, right? Because when you have a lot of precipitation, when you have a lot of precipitation, that is going to make the water fresher, less salty, right? Does that make sense? Because remember the rain that falls, thank goodness the rain is fresh water. Wouldn't it be horrible if salt water fell?
Yes.
Horrible. Everything would be rusted and destroyed, and the plants would wither and die, and it'd be horrible. But yeah, but you know, the water that falls is fresh water. So I hope you can remember, maybe we go back a little bit. I want you to remember this. We looked at this. Remember we talked about evaporation, places where evaporation outpaces precipitation? Remember we talked about that? So there are certain places, we'll learn later in this course why we see these patterns the way that we do. But evaporation is the opposite of precipitation. So evaporation is going to make the water saltier. Right? It's going to make the water saltier. So notice that at the equator, we get more precipitation, less evaporation. Whereas at these tropic lines around the tropics, we get more evaporation. And notice, I hope you can see a direct correspondence between this and salinity map. And actually, I think later I actually put these two things side by side. So you see how they're right in the tropics. There's a kick up in salinity. That's because there's more evaporation right there. Okay. There's a lot of evaporation in the Mediterranean. You know, it's a hot place, right? Look in the Persian Gulf and the Red Sea. There's like around Saudi Arabia. It's a lot of evaporation, right? It's like a desert environment. It's lots of evaporation. So that makes the salinity higher. Okay, another thing that controls salinity. Think about this in the polar areas, polar regions. Ice formation and ice melting, right? That's going to play a role too. So precipitation over the ocean is going to make the water fresher, less salty. Precipitation is greatest around the equator. So this is a global map of precipitation rates, and you can see that the most precipitation you get is around the equator. And that's why you get all the rainforests are around the equator.
What puts all that salt in the ocean? Like, does it come from rocks? Right?
Yeah, basically it comes from rocks. It's just the stream runoff picks up a lot of salt from the rocks and also from volcanic outgassing. And it ends up in the ocean, and the water can evaporate and return back to land, but the salt can't. Because you know that when you evaporate water, the salt stays. So it just continually concentrates the salt in the ocean. Evaporation makes the ocean saltier. So in desert areas, the water is going to be usually saltier. So you actually see like the salinity around the Sahara Desert, you know, right off the coast of the Sahara Desert is higher. It's more of a evaporative environment. Okay, evaporation makes it saltier. It's because when you evaporate salt water, the water leaves, but the salt stays. Okay. So again, you notice that if you compare evaporation, this is the evaporation minus precipitation graph I showed you before, evaporation minus precipitation map, I should say. And notice that it looks pretty similar in some areas to the salinity map. I hope you can see that, right? So like this blotch right here, this blotch right here in the North Atlantic and this blotch right here in the South Atlantic corresponds to that and to that, right, for salinity. Does that all make sense to you? Okay. So that's an evaporation minus precipitation map. So the red areas have more evaporation. Okay. And you can see that corresponds. Looking in the Mediterranean and the Persian Gulf, right? There's a lot of evaporation. So you can see it's relatively salty water there. Okay. All right. Another thing that affects the surface salinity is ice formation and ice melting. Now here's a thought experiment for you. Let's say you got some salt water and you put it, say you got let's say like a cooler, Yeah, you get a cooler, a small cooler. You fill it with salt water, and you put that small cooler in your freezer. And then you let the surface kind of freeze, and you break that ice off, and you take it out. What do you think? Do you think that that ice that formed from the salt water, do you think that ice would be salty? It would be relatively fresh water. Okay? It would be relatively fresh water. So, another factor that comes into play here is that when the sea ice forms, the ice is going to suck out the fresh water and it's going to leave behind the saltier water. Does that make sense? So if I took a cooler, I filled it with salt water, I let half of it freeze, okay? The ice would be relatively fresh, and the residual water, the water that's left behind that did not freeze yet, will be even saltier than when I started off, because the salt gets left behind. Okay, does that all make sense? Is everybody with me on that? Okay, so in the polar regions, that's a big deal. Okay, so what happens is that the ice forms, and it leaves behind saltier water. Now, this is a thing that happens, and again, it's going to become a big deal in this class. What is going to happen to that salty water when it's left over from the ice? What happens to really salty water when it sinks because it's denser? So what's going to happen is it's just going to sink. All the salt water is going to sink. Okay? So the ice is going to form, and the salt water that gets left behind will just sink to the bottom. Okay? So there you go. Pure water, it freezes. Salt water will turn into kind of a slush, and then it's going to form pure ice with no salt in it, and it's going to leave the salt behind. Okay? So when ice forms from seawater, it leaves salt behind. This makes the ocean saltier when ice forms and less salty when it melts. And so the opposite will happen when it melts. So I want you to notice something. This is kind of cool. Notice around the poles, the water is actually less salty. The reason it is less salty is because when the ice melts, it freshens up the water and it stays on top. Because remember that fresh water is less dense, right? But when ice formation occurs, it leaves behind saltier water, but that saltier water immediately sinks. Okay? The saltiest water in the ocean is the bottom waters of the Arctic and Antarctic. They are the saltiest waters in the whole ocean. They're absolutely saturated with salt. They're the saltiest waters at the bottom because it sinks right down to the bottom. So that leaves the polar regions relatively fresh, relatively fresher. So sea ice melting is why surface salinities are abnormally fresh in the Arctic Circle. And why is that? Why is it fresh? It's because that salt water sinks. So when the salt water sinks, the briny water that's left behind, the salty water, just sinks right to the bottom. And this is where the bottom of the Arctic is where you get the salt-saturated, saltiest water in the ocean. It sits right down there on the bottom of the Arctic. Okay, so does that all that stuff make sense? All right, now one last thing that affects surface salinities that I want you to put down for number 3 is river runoff. Okay, river runoff makes minor effects. So I can show you this right here. You can see little areas, like if you look right around Louisiana, right there, do you see that little bit of fresh water? It's kind of little purple right there. That's the Mississippi River coming in. Makes the water relatively fresh. Okay. And you see right here, this is where the Amazon River is coming in. And right here, this is where the Ganges River comes in. So where there are rivers, you'll get these little local effects from the runoff from the river, making it relatively fresh. Okay. So that's another thing that affects it. All right? So Now we've looked at surface processes. Okay, we looked at what makes the ocean water saltier or fresher at the surface. But now I want to show you a little bit what happens with depth. Okay, what happens with depth? So this is salinity. Okay. Now I really urge you to pay attention to this part because it gets kind of complicated, and on the test I will ask you very specific things about like what happens to salinity with depth when you're at this latitude. What happens when you're at that latitude, right? So I get very specific on the test. So pay special attention right now, okay? This is a chart of salinity with depth, okay? Now, at the surface, everything is different, right? You notice how everything's different. The green line is the high latitude, that's the poles, okay? Arctic, Antarctic. The red line is the, equator, okay? The blue line is in the tropics. So let me ask you all, where is the saltiest surface water? Tropics, poles, or equator? In the tropics. So that might be it's kind of counterintuitive because you might just think the hottest place is going to be the saltiest water, and it's not. The hottest place is the equator. The tropics is not as hot, but it has more evaporation. Okay, and if that doesn't make any sense to you right now, it will when we talk about atmospheric circulation. Okay, global atmospheric circulation. I'll explain all that, why that is. But the tropics have the saltiest surface water. Now notice that when we get down to 4,000 meters deep, how much are they different? Are they different, or do they all converge and then become the same? Yeah, they all become the same, okay? So remember that at depth, everything will converge and become the same, okay? Now you'll notice that there is a part, especially in the tropics, there's a part of the tropics near the surface where there is a dramatic change of salinity with depth. So you go from about 3.65 all the way to 3.55 in just a matter of, I don't know, like 500 meters or something. So it's maybe less than that. Maybe that's like 400 meters, okay? So there's a dramatic change. Do you see the slope of this thing where it almost flatlines and it just goes, you know? That shows that there's a dramatic change in salinity with depth. That dramatic change in salinity with depth is called the halocline. Halo stands for salt. Halo means salt. Cline means a slope. So it's the place where there's a very high slope, a very high change to salinity levels, okay? So what happens to salinity with depth in the tropics and in the equatorial waters? It goes down with depth, right? So in the equator and in the tropics, salinity decreases with depth. Look what happens, though, in the poles. How does salinity change with depth in the poles? Does it go up or down or stay the same? What's that? It slightly increases. Okay, it slightly increases. And why does it slightly increase at the poles with depth? Because all the salt water sinks to the bottom during ice formation. But when the ice melts, in the summer, it doesn't sink. It hangs around on top. So the salt water that forms in the winter time sinks, but the fresh water that forms in the summertime stays on top. So that actually makes it saltier on top in the Arctic and less salty on top in the Arctic, and then it gets saltier as you go down. Okay, so be prepared for that, because on the test I could ask you very specific questions about this. How does salinity change with depth in the Arctic? I could ask you a question like that. So does that make sense? See, that's why I'm trying to get you all to pay attention right now, because there's just a lot of little details here. So it gets saltier. Okay, what if I asked the question on the test, I said, how does salinity change with depth in the tropics? Then what would you say?
It decreases.
Yeah, it decreases. And what if I asked on the test, what do you call that dramatic change in? Yes. Okay. What happens to salinity with depth at high latitudes, and why does that happen? We just answered that, right? Number 5. Oh, sorry. What happens to salinity with depth at high latitudes? That's the poles. So salinity goes up with depth, right? And that happens because of the ice formation during winter time. That salty water sinks as soon as it forms. Number 6, what do you call the dramatic change in salinity with depth near the surface water? Halocline. All right, everything makes sense so far? Got that? I'm going to go on now to temperature. Okay, here's temperature. So we're going to do the exact same thing, but we're going to do it now with temperature instead of salinity, okay? So at the poles, how does temperature change with depth? It doesn't. It's cold on top, and it's just as cold at the bottom. Because as soon as you get, because it's you know, it's like 0 degrees at the surface, it's freezing. And then if you were to try to form some ice, the ice would just rise to the top, right? So it's not going to get colder with depth. It's just going to be cold at the top, cold at the bottom. That's why that salty water sinks. Because there's no change in temperature with depth in the Arctic Ocean. Okay? Notice though, look how things change in the tropics and in the equator. It's very hot on top, right? But man, look, you don't have to go very deep, and look how the temperature plummets. It goes from 25 degrees, that's like 80, maybe like 83 degree water, okay? 83 degrees Fahrenheit. And it plummets. You don't have to go down very much, maybe 100 meters. And it plummets all the way down to maybe like what, 12 degrees Celsius? 12 degrees Celsius is kind of chilly. Okay? It's chilly. It's probably like outside right now it's probably 12 degrees Celsius, right? So it gets cold fast at the equator. And you know, the same thing too with the tropics, right? It gets cold pretty fast in the tropics too. So that's why in the tropics, evaporation forms salty water, but that salty water doesn't sink. It can't sink because it's too hot. It's too hot. Remember that just the hot air balloon, right? The hot water rises. So even though it's salty, it's buoyed up because it's hot water. It's hot, salty water. So it can't sink, different than the poles. When salty water forms at the surface in the poles, it can sink because there's no temperature difference. There's no thermocline, okay? So this dramatic change in the temperature of the water with depth is called the thermocline. A strong thermocline is going to keep surface water stable. It's going to prevent surface water from sinking. A strong thermocline is going to prevent surface water from sinking. The tropics and the equator have a strong thermocline, right? You see how much it changes with just a little bit of depth. You go down, it changes a lot. It gets cold really fast. But at the poles, there is no thermocline. Poles have no thermocline. All right, number 7 is thermocline. That's all you got to put. Thermocline. Okay, so number 8 says, how does temperature change with depth at the equator and the tropics? It drops, it goes down, right? Now, why does that happen? Why does it get colder as you go down? Pressure, it's a good guess, but that's not quite right. So when you go down, well, think about it this way. What's heating everything up at the surface?
The sun.
The sun. Is there a lot of sunlight as you go down?
No.
So that's why. And think about this too. That hot water that's at the surface can't mix. It can't go down because it's buoyed up by its it has a low density. It's hot, and it can't. It wants to go down, but it can't. And that is, I know, sorry, this can get very complex, but actually you'll notice that the thermocline is not as strong in the tropics, and it's because that water on the surface is saltier, so it's a little bit denser, so it can mix a little bit. But the equator, boy, there's no mixing, right? That hot water just stays on top because it's fresh and it's hot and it's not going down. But over here, the tropics, it's hot, but it's also salty. And so it can mix a little bit with the stuff below. And so that kind of decreases its thermocline. Does that make sense? You get it? Yeah.
The equator does not mix. The tropics mix a little. And then the poles.
Yeah, and then the poles, it's crazy because surface water will just go all the way down to the bottom. It mixes like crazy because the salty water just goes all the way down to the bottom. Okay. So we did number 7. How does temperature change with depth at the equator and the tropics? Why does that trend occur? We answered that. So how does temperature change with depth at the poles? Why does that trend occur? I think we explained that, right? Y'all understand that? And then, now we got to get into the next thing. So we did the halocline. We did the thermocline. Now we have to do the pycnocline. Pycnocline. Pycnocline is the change in density with depth. In relatively low latitudes, so the tropics and the equator, density goes up with depth, and then it hits a certain point, about 1,000 meters depth, and then there's no change. You see how there's no change from 1,000 meters down to 4,000 meters. There's no change. But there's a dramatic change going from the surface to about maybe 1,000 meters depth. There's a pretty strong change. That's called the pycnocline, change in density with depth. High latitudes, there's no pycnocline because the water up here is cold, the water down here is cold, and that's it. So these are mostly controlled by the shape of these lines. It's mostly controlled by the temperature profile. Mostly controlled by the temperature profile. Okay. All right, so number 11 on the back page, it says, how does density change with depth at the poles versus lower latitude waters? So how does density change with depth at the poles versus lower latitude waters? And all you really have to say there is there's a pycnocline at the lower latitudes, but there's no pycnocline at the high latitudes. And the reason for that is that there's no temperature. Really, you could say the reason for that is there's no thermocline. There's no thermocline in the poles polar high latitude waters, and there's a strong thermocline in the low latitude waters. There's a strong change with temperature because it's mostly being controlled. The density is mostly being controlled by the temperature. So that's kind of what you have to explain there for number 11, okay? So do we get all this? Is this all coming together and making sense? It's a lot of kind of interconnected parts and moving parts to this thermocline and pycnocline and the halocline, and they're all kind of connected together. So it's complicated. All right, are we good now? We're all caught up to number 12 now? Okay. I'm going to go on. One kind of last thing, kind of another last property I wanted to talk about with water is thermal expansion. So, a lot of people, like I said, are concerned about rising sea levels. We'll talk a lot about rising sea levels in this class, and it's actually really interesting because some places are rising, some places are sinking. And that's natural and predicted. So, and we'll explain, why some places rise, why some places sink. Now, I mentioned before that glacial ice melting has something to do. Actually, somebody wrote a discussion post. Somebody did a discussion post on it. Was it? Yeah, it was. And we talked. You talked about this actually, right? Remember, you talked about glacial ice as part of it, but the other part of it is thermal expansion of water, right? Because when water, I remember you mentioned that in the post. When the water gets hotter, like a lot of materials, it expands. So that's another thing that makes you could imagine if your 5,000 meter column of water expanded a little bit, it would cause the sea level to rise. So if you were to raise the temperature of the whole water column 1 degree Celsius, now 1 degree Celsius, I know that doesn't sound like much, it's kind of a lot. That would be a huge deal. But it would increase the sea levels by 26 centimeters, which is a lot. That's like what, over 10 inches. I guess maybe that's not that much, but it's something. I mean, it's 10 inches. I guess it'd be a big deal if you were living in. I always forget how to say the name of this country. It's a country. What's that?
Sikilis.
Sikilis? What is it?
Sikilis.
Sikilis?
I had a boss who was from.
Oh, really?
So he taught me how to say.
Oh, Sikilis. Okay. Well, there you go. But it has an average, land elevation. It's very low. So that 10 inches could be a big deal for that. Corpus Christi, probably. Gosh, under the bridge. That area under the bridge there. It's really that could be problems for that. It rose 10 inches, but over here, Del Mar, I think we're okay. Okay. Anyway, I got light in the ocean. It's the next part. All right, so light, remember that light is a wave. It's a wave. Do y'all remember this little guy, this little bugger, the electromagnetic spectrum? So electromagnetic spectrum gives the spectrum of light waves, okay? And you know that at this end, at the blue end, blue indigo ultraviolet end, you have a higher frequency and you have a shorter wavelength. So do you see how the waves are kind of jammed up closer together? A lower wavelength here. And then you have a higher wavelength when you go over here to the red, okay? So red is actually lower energy light. You know how everybody's concerned about what kind of light gives you cancer? Is it the red light? No, it's the ultraviolet light, right? So it's the ultraviolet light that can give you skin cancer and things like that, right? Because that's actually a higher energy light. There's a lot more energy contained in it because it's a higher frequency and a shorter wavelength. So there's actually more energy photon per photon in ultraviolet light than there is in red light. Okay. So the light that you can see is there's lots of light you can't see, right? The world is full of light you can't see. But the light that you can see, we have lower wavelength, which is red, orange, yellow. Higher wavelength is a blue, indigo, violet. Right? Now, why is this water blue? You know how they always say water's blue, right? And you look at the ocean, it often appears blue. Okay? So why is it blue? It's blue because the light that comes from space, it comes from the sun, is a mixture of every different light, right? So like you see the rainbow or you see a prism, you see that sunlight is actually composed of all these different colors. Okay, so when you see a mixture of light, you see kind of plain white light. But what happens is that water actually it doesn't treat all wavelengths the same way. It's much more effective. Water happens to be much more effective at scattering blue light. So water is very good at scattering blue light. So the the light that ends up reflecting back to your eye ends up being overwhelmingly blue. So that's why water often appears blue. Okay. So water refracts light. You can see, remember, this is what I was showing you with the laser pointer, right? Goes through, it bends the light waves, right? I already showed you, this is everything I showed you already with the laser pointer and the water tank in the beginning of class. Okay. So that water actually bends and refracts the light. So ocean water scatters, absorbs, and refracts light, and that limits the ability of sunlight to penetrate into the water. So we have a photic zone, which is near the surface. That's where there's a lot of sunlight. But you don't really have to go too deep, and then light starts to just go down quickly to a trickle. Right? It gets darker and darker as you go down. Most of the vast majority of life in the ocean lives in that photic zone. The vast majority, probably 90% or more of it lives in the photic zone. So different wavelengths of light are absorbed at different rates in the ocean water. So that means that as you go down deeper and deeper, you'll notice that that colors actually change. So this is kind of a cool experiment you can do. So let's say you take this toy with all these different rainbow colors, right? And you take it down to 91 feet, which is really not that deep, right? That's really kind of still the surface water. And look how the colors change. Right? Very different, right? And that's because certain wavelengths are absorbed better than other wavelengths in water. Blue light is heavily scattered, but even though blue light is heavily scattered, blue wavelengths are scattered by the water. They're more penetrative, so they can penetrate pretty far. So you'll notice that blue and violet don't really change that much. However, red just gets absorbed right away. Red does not get very far down at all into the water. So look at how look at this red one. Isn't that crazy? It's almost black. Do you see that? I mean, it's really dark. It's one of the darkest ones. I mean, probably second to black, actual black, it's like the second darkest, right? Or maybe the third darkest. So red just does not make it very far down into the water. So this is, by the way, did you ever notice how some seaweeds and things like that, they're not like, you would, on the surface, right, our trees, they're green, right? They're green. But you might notice that that's not true with seaweeds. Some seaweed's green, but a lot of seaweed, especially if it's deep in the water, is not green anymore. And that's because, for example, there's not much red light, so it's not going to be the chlorophylls and things like that are not going to be geared towards absorbing any red light. Doesn't want any red light because there is no red light, right? So a lot of that red light is reflected back, and that's why a lot of seaweed will look like brownish, kind of reddish brownish. And probably you've seen things like that, kind of reddish brownish seaweeds. Instead of you might assume without knowing anything that everything would be green, just like all the plants on the surface, but they're not. This is a weird thing. that diver cut his knuckles. Do y'all see what's happening? That scuba diver, it appears green, right? He has green blood. No. It's just because there's no red light makes it down that deep, so you can't see the red that's reflected from your blood. Okay, so like I said, red gets absorbed right away. Yellows they go down a little bit deeper, maybe only 10 meters. But look at red. Red doesn't make it down hardly at all. It gets absorbed right away by the water. Water is just great at absorbing red light. Green makes it down pretty far, but blue makes it down the furthest. But blue also gets scattered easily. So blue is actually preferentially scattered by the light, but it does penetrate far. So that's why, again, when I went back to this, you can see that the blue colors, the blue-purple colors, don't really change very much. They still look kind of bluish, purplish. Green doesn't change too much. Now, you know that not all water, especially here in Corpus Christi, looks blue. But so what are some things that change the color of the water? Here's a kind of a crazy picture. Do you see all this? This is actually a pink lake. Some lakes are pink. Isn't that weird? You can actually, let me see if I have any. This is actually not that great of a picture. Let me show you. There's some really crazy ones. Oh, I don't know if I want to mess with this because it'll mess with the owl. I don't want to make the owl angry. I won't do it. But you can look this up online. Look up like pink lakes, and they get like hot pink. I mean, they're like pink like. I'm not going to tell names, but they're really pink. But that pink, that's actually from phytoplankton. So it happens to be from a certain type of phytoplankton. You might have seen things like this, red algal blooms, right? So again, that's all from different phytoplankton. And again, why would that algae, that photosynthetic algae, be red? It's red because it doesn't use the red light, right? It wants to absorb everything but red. So it reflects the red light back because it doesn't care about red, because red light just doesn't make it very far into the ocean. So a lot of algae is red, right? You've probably heard of things like red tides. Has anyone ever heard of that? Red tides. And then sometimes you get, oh, that's gross. That's totally gross looking. I'm surprised that doesn't happen here. But I've never seen it look like this, but this is in Texas. That's a green, algal bloom. So sometimes algal blooms can make it look different colors. Also, another thing I wanted to point out to you, do you ever see this, like, a lot of sea foam? And a lot of people think like, ooh, it's pollution. But it's often not pollution. A lot of that sea foam is actually from all the organic matter. If there is an algal bloom, it's from a lot of the organic matter that's in the water. So actually that can be kind of natural. But pollution can cause it too, but it can also be natural if there's a copious amount of algae. Okay. All right, so last thing I want to talk about here is sound in the ocean. So did I hit everything? Up to number 20, did I get everything? Okay, so number 20 is, this is misspelled. Do sound waves, you have to cross out the ES, do sound waves travel through seawater? Okay, what's that? So what do you think? Do you think sound waves go through, you can tell that it goes through air, because I'm talking to you. But do the sound waves go through water? Has anyone ever put their head underwater and hear? Can you hear anything when you're under there? Yeah, you can kind of hear muffled. Yeah, but you can hear stuff, right? You can hear stuff. So sound does travel through water. Okay. The speed of sound. Remember that we actually use that in echo sounding, right? So it definitely travels through water. And remember that the speed of sound actually is affected by some things like temperature, pressure, salinity. They all affect things. And what's kind of cool is that there's actually a certain depth that you want to. This is kind of a weird thing, but there's a very certain depth in the ocean that sound waves will travel the furthest. And that depth range is actually called, appropriately abbreviated, so far. so far. And but I'm not kidding. I'm glad that they did something in a useful abbreviation. And I can't even remember what so far stands for. But it's actually a certain depth in the ocean. You can see 500 to 1,000 meters deep, where sound waves will travel the furthest. And it's because of, well, I'm going to show you in a minute why. So sound waves, just like light waves, are bent and refracted. So when it goes from a body of water where it has like a higher sound speed to a lower sound speed, it'll actually bend the sound waves. And so what happens, this is actually kind of crazy. If you emit a sound wave, the sound waves, can you all see what's going on? This boat is emitting a sonar wave, a sound wave, okay? And it tries to go down, but then it's bent back up and returns back to the surface. And that's happening because of refraction. That happens because of refraction. So when boats have a sonar is just, it's almost like it's like an echo finder or a fish finder or something like that, okay? The ships that have sonar, there's actually a shadow zone that they cannot detect an enemy submarine. Do you all see that? Because the sound waves try to go down, but they're refracted by changes in the sound speed. That they actually hit that. What it's hitting is the thermocline. Because it's going to change. The temperature profile is going to change the speed of sound, and it's going to refract the waves. And so you don't have to memorize, obviously, like the path of sound, and you don't have to worry about that. But I just generally want you to know that sound is refracted through the ocean in a very complicated way, and it actually ends up being pretty important because this. So, like I said, if you emit a sound at the SOFAR depth of 1,000 to 500 to 1,000 meters, notice how that sound wave can actually travel maximum distance through the ocean without being refracted. Whereas if you try to make something at the surface, the sound wave will get refracted and bent back to the surface. And so it actually won't travel that far. So if you want to make sure that a sound wave or a sonar goes as far as possible, it has to be at about 500 to 1,000 meters depth. And that's the SOFAR channel. So like I said, if you have sonar that's being emitted from on the surface from a ship, there'll actually be, like I said, a shadow zone where the waves are refracted away from this shadow zone. So the refracted waves don't detect here. So if you're enemy submarines, if you're a submarine captain, you're very keen on things like this, right? You're paying attention to things like a shadow zone. Okay. So that's how you would avoid detection by an enemy surface ship, right? So anyway, but kind of the main thing I just want you to see in here is that sound waves are refracted and bent, and they go in a very unintuitive way. They're reflected in a very unintuitive way around the depths of the ocean. I mean, you can see just how complicated that all is, right? So that's all I have for you. It's 12:14, so I'll let you all go. And guess what? It's spring break now. Well, it's spring break, I guess.
Can you also 21 for me?
Sure, yeah. Right into 21, and then what always happens to a wave when it enters a medium with a different propagation speed? It is refracted. Number 21 is very important, folks, so just make sure, if it doesn't make sense to you, I don't know, meditate on it and try to understand it, because it's just really important. It happens to everything. Okay, I'm going to turn off the owl.